And okay, so welcome everybody. Happy Friday. Dean was here now. So this week we have Professor Razvan Teodorescu speaking to us about quantum field theory. So Razvan.
Yep. Okay. Thank you all for coming. Thank you for having me here. We thought about having something like this in Nathan's seminar for some time, and I thought he was going to do it. Seems it's not, he's just too modest. So I decided to share my ignorance, so you can blame me for whatever. Yeah, the broad subject is quantum field theory, which is of course impossible to cover. But what we can do at least is to start talking about it. And definitely my aim would be to provide an introduction to the subject. There are many good books. I am fortunate enough to have talked to some of the people who wrote such books. And what I heard all of them saying is that in every single instance, people started off with a very generous idea of writing down a complete story, at least covering everything in the same amount of detail, and then kind of halfway through they realized they actually have a life to live and they switch to shortened version. So which is why these books are only around 1,000 pages long, most of them. So what I'm trying to say is that you are more than welcome. Actually, it's highly advisable that you can look through older, newer textbooks on the topic. If I were to make recommendations on a number of different criteria, I would say the shortest, and from that point of view, the brightest choice would be a book, a pamphlet-like book by Bjorken and Drell, which is extremely condensed. It's really barely an introduction to the introduction, but it does the job. And on the opposite end, it's the monumental 3 volume of Steven Weinberg that's clocking around 3,000 pages. And it's by Weinberg that kind of says it all. So in between these, you'll have a variety of books that you can think of. A personal favorite, in the sense that if you survive that, nothing will kill you, is a book by Bogolyubov-Shirkov, published in 1959, which proves how the beauty of a subject survives horrible exposition skills. So I don't know where I place him here, but let me get started somewhere. And as always, most of you do know me in person, so you know I welcome and encourage interruptions, even if they're not on the subject. So getting started, this is actually a topic that, what are these 3 books? I only mentioned 2 authors. I think Bjorken and Drell is Introduction to Quantum Field Theory. That's the actual title. Steven Weinberg, that's the 3-volume series. It's simply Foundations of Quantum Field Theory. I'm ashamed to say I don't remember, although someone gifted me that series. It's somewhere.
The titles in chat.
Okay, yeah. Right, so blank screen. I'm not writing anything yet, but I'm talking. Can you hear me?
Yeah, I was just going to suggest you write it down in chat, because some of us have difficulty making out these names.
Oh, okay, sure, absolutely.
Thank you.
I will do that. But let me get started with the actual content then. I was just saying that there is some good books that one can spend time with, and it's no worse than trying to read Moby Dick. That's all. Anyway, so yeah, quantum field theory. Which one of the 2 Bjorken and Drell field theoretic? Let me read the whole thing because I'm not seeing it. The shorter one, David. I'm joking. I think it's introduction too, right? I should check. Okay. Anyway, so intro to QFT. Okay. Yes, I've heard worse, but I can't say that yet. So QFT hereafter shall mean quantum field theory. And I think it's only appropriate to cover CFT first, which in this context will stand for classical field theory, unlike what someone like Nathan might think it means. So Intro to QFT has to start from classical. And that is, of course, another name for everything that was interesting in theoretical physics pre-relativity theory. So I'll just say it's not non-relativistic, it's pre-relativistic. By the way, how does the writing come through? Is there a delay? Does it feel like?
There's a slight delay, but it's not anything that comes up as an issue.
Excellent, excellent. Thank you. So I'm saying it's pre-relativistic because without knowing it, they were, of course, developing totally, fully relativistic theories. And by they, I mean here in particular Maxwell, but also collectively the people who are developing Hamiltonian mechanics. So this is stuff up to, let's say, including the very beginning of 20th century, at least up to 1901. Just to pick an year. So that means two different things. Classical field theory fully developed would mean Lagrangian mechanics for continua. I'm not going to write that down because we'll get to see that. And what seemed to those people at the time to be a completely different story, Maxwell's equations. Right, so again, this is supposed to be choosing a path through a huge subject that's necessarily going to cover both topics from physics, more specifically theoretical physics, and mathematics. It's going to be mostly mathematics, but kind of in the style of how Richard Feynman would see it. So I have to ask and prompt this. If there are questions as in what exactly is any of these things, does it any of these things stand for, please let me know, because I would hate to lose people as early as 5 minutes into the talk. So are there any questions so far what I'm talking about, in the sense that you've never heard of these things? Okay, hopefully no one is asking because they don't feel the need to. All right, so let me recall the context of, now switching a little bit to math, let me recall the context of Lagrangian mechanics first. So this stands for the following. We start by thinking of a system that can be broken down into what we can picture a finite number of point masses, which is the kind of oxymoron you'd hear from a physicist. So the idea is that geometrically speaking, you only have a finite number of points. And if you knew the location in space of all those points in a certain interval in time, then you declare yourself satisfied because you know the state of the system. So a mechanical state in this sense would be, if we think we live in 3 dimensions, a position in physical space, 3-dimensional space, which will then double, because besides this, we discover, simply because the way Hamilton's equations look, that we need another 3 real parameters to fully describe the mechanical state, something we're going to call momenta, which generalizes the notion of velocity, if you wish. So we have a point in R6, and if we have n such points altogether, of course, there's going to carry through. That's therefore r to the power 6n. Any questions? Right, describing a state of the system for this simplest mechanical system simply says that you are going to have a function that tells you, say is defined on the interval t0, t1 larger than t0, and this stands for time, taking values into R6n. And of course, the function has to be smooth enough so that we can do calculus, going back to Newton. And we're going to break this down into 2 groups. So the 6n dimensional vector basically consists of something I'm going to call Q1 to Q3n, P1, P3n, 2 equal length vectors, eraser. Collectively put into this 6n dimensional vector, telling you where you are at time t between initial time and final time of this dynamical process. So initial. Right, so the equations of motion that describe a system like that, in the case where we have a structure that is compatible to what we call Hamiltonian mechanics, are first order ordinary differential equations. I will not write those down because we don't necessarily know that that's the situation we're in. So we're going to look at the description that is a little bit more general, which is what I refer to as Lagrangian mechanics. Going to a field theoretic generalization means we're going to consider the number of these mechanical points to go to infinity in just the right way so that this infinite dimensional space we will arrive at makes sense. So that's what I'm going to describe in the next 1 or 2 slides. So again, no questions so far. I'm going to add here, this is a mechanical state, Newtonian mechanical state, really. And by that, I simply mean state as it's defined when it pertains to mechanics. Right, so classical field theory somehow, starting from this atomistic description of mechanical systems, prescribes that you are going to have, quite generally, a function that I'm going to refer to as Lagrangian density. So these are already definitions. Lagrangian density, curly L, it's not straight L, hopefully one can distinguish between these two, which depends on what I'll be referring to as coordinates, as in you can think of them as generalizations of the Cartesian coordinates, collectively denoted as Q alpha. Alpha is an index. Their derivatives, first order derivatives in the parameter called time, so all the Q alphas dots, and could be explicitly, but certainly implicitly on time itself. This is this further parameter t that is itself the only two independent variable in this problem. So I have a Lagrangian density which returns to me a real value. So this is defined on, now I'm going to make a choice to distinguish from the previous row. It's defined on R2n plus 1. Again, the 2n stands for this collection of real numbers, and of course the degree of freedom at the very end has to do with time itself, and takes values into R. And I'm going to integrate in a region in space. This relates to space. 1 second. Color. Oops. Getting me to what I call Lagrange function for the system. So Lagrangian density and Lagrange function. Straight L, which now taken at face value only depends on time, will be the integral of the Lagrangian density against a volume form in space. dq alpha. Put a vector over it to denote by that the generalized volume form in Rn. So dqn, dq alpha in Rn is volume. Any questions? Okay, Nathan, do you think I'm going too fast?
I think it's okay. So I think maybe a point of clarification. So to connect back to, well, classical Lagrangian mechanics.
That's what I'm developing. So I'm not sure if
okay, so let's back. So for Lagrange function for just a single point particle or collection of point particles would be what? The Lagrangian density is a sum of
delta functions.
Delta functions. Yeah.
Yeah.
Okay.
Yeah.
So
we can still integrate. We're going to get a point evaluation. Correct. But for field theory proper, you need to have this truly defined in a set that has something like full measure in volume, in the sense of volume, in the space coordinates, q1 through qn. So if we think about applying this description to for something like water waves, right? We're talking about a region in space that's occupied. You think of it as being a continuous function by this density of mass or matter, and with it comes this density of Lagrangian. Is this a good picture already? Yep. Or the simplest proper classical field configuration would be a string. I'm going to provide it as an example right now. How about that? Right. So example. Mechanical string, ideal string, which I hope doesn't get anybody's hopes up. This is not those strings that we might end up talking about at some point. So this is the case where you have L itself defined on R times R, one space coordinate, one time coordinate, real valued. And it so happens that we get to writing this down because we think like Newton in the sense of breaking down a continuous field into what we think of as material points and picturing the interactions between these points by mapping them to very simple mechanical systems like an elastic force for restoration, so a spring. So if you think of this as being made up of these massive points connected by springs, you arrive at the following continuous description. L, is going to be the derivative of that one spatial coordinate, q dot squared, minus, and this might be a parameter that depends on the material. I'm going to call it omega for frequency if you want. It's some real number that physics gives us. And that's multiplying the first order, the first contribution, the first perturbation from equilibrium that matters. This is how we arrive at that. Partial q with respect to x squared. So I'm thinking here of q being the field itself, x and t are its coordinates. It might be a bit confusing. I'm trying not to. So q of x and t is a point evaluation of this.
Real quick, Professor Razvan, the screen's cut off at the bottom.
Okay, so can you see up to here?
It cuts off below that. Yes. Right
below that? Okay,
yes.
I got it. I will turn the page and can rewrite this stuff. Okay?
Thank you.
Thank you. Turn the page, how that can reach. It's just never done this before, Nathan. Do I just treat it as a whiteboard?
How do you turn the page?
Yeah.
I don't know on the app you're on. So maybe what app are you using? I just saw one.
There you go. Got it. Thanks. So I'll rewrite the details of this example. I'm going to take q defined on R times R. It's itself real valued. So I'm writing q of x and t. In this case, for the string will denote the height with respect to what would be a completely flat equilibrium configuration of the string, fully taut stationary string, and this is measuring the displacement, let's say on something like a vertical direction, perpendicular to this equilibrium position. So this is height. And here's a picture. Yeah, very illuminating. So that would be the equilibrium position. And if you have a generic state of this system, then at x and at time t, q of x and t measures that displacement, which doesn't have to be positive. It could very well be negative. And then you picture something like this for the actual configuration that might be more recognizable to most people. I'm pushing it. It's supposed to be nice and smooth. You get the idea. Okay, is this clear to everybody? Well, not. Anyway, so I was saying that for this system, just by thinking of it being made up of points connected by springs, and that one parameter that describes how rigid those springs are is the parameter omega, gets us to the following Lagrange function. L, if I'm thinking about an infinite string, just to make things easy, will be the integral from over space from minus infinity to infinity of the Lagrange density against the one spatial coordinate. And in this case, it's just what did I say earlier? Q dot squared minus omega squared over 2 partial q in x squared. Integrate with respect to x at a moment t, given moment t. Right, so obviously this can be generalized right away for having degrees of freedom not only in one spatial coordinate x, but let's say x, y, and z, because that's more familiar to us. And to make it more realistic as well, I'm going to say that we're integrating in a finite volume rather than from minus infinity to plus infinity. So again, if I try to sketch what I'm about to write next, the configuration I'm building towards something like this. At a certain moment in time, so this is my time coordinate, at a certain moment in, hyperplane perpendicular to this time coordinate. And in our case, the one I'm describing here, this is simply R3. And I have some region of interest here, something corresponding to it in the other slice, and a flow in time giving me at every moment between these t0 moments in time t0 and t1 corresponding configuration in this spatial slice R3 in this case. So of course, if you were to connect them by continuous paths, we end up with something like that. There you go. Call me Picasso. So if this example is clear enough, I'm going to just write down the equations that characterize this evolution and come to us from a postulate, from an axiom we propose ourselves simply because we notice time and again that it seems to be the one truth that holds in every single instance we care about. And it goes the following way. We're going to integrate for any particular path, basically definitions. What I've sketched can be understood as a graphical representation of the following. So if I have gamma, a path, it's easiest to think about one point only evolving in time and being found at every moment in time in some copy, Euclidean space Rn. But it's going to be this functional path I'm talking about, q of t from t0 to t1. Q is that function. And for each such particular choice of the function q of t, we're going to have the action functional that returns for that particular path. I'm going to write this on action. And is described as it's given by the integral from t0 to t1 Lagrange function dt, or obviously integral from t0 to t1, broadly understood as a distribution integrated in fullness in the spatial part of the configuration space, Lagrange density dx dt. And that's only meaningful if we know that we started somewhere. So I'm going back to the picture now and adding something. Here, in order for us to be able to say anything about anything, we have to be given the at least the initial configuration. So we need to know what were all these q alphas at t0. And as it turns out, the variational principle I'm building towards also requires me to specify where I'm expected to end up. Q0 of T1. These are boundary conditions of sorts if you only think about, like I said, proper spatial generalized coordinates Q alpha. As a matter of fact, it comes for free, but they should not be counted along with these, that we should also know what were initial values of the first order derivatives in time of the same coordinates. So in different color, also be provided Q alpha dot at T0. But that's all there is. These are all initial value conditions. Altogether now, it's kind of like a mixed problem because we have partial boundary values conditions and initial values in first order derivatives, but you can't require anything else. You can't impose anything else. For instance, you couldn't tell the system what Q alpha dot at T1 should be. That will be outcome of solving the problem. So with that in mind, yep.
Maybe a point of clarification or question or a combination of both.
Yes, please.
So first, alpha for you is now a continuous index, yeah? It's indexed by points in R3, essentially.
I'm sorry, Q alpha you said?
So alpha, the index alpha, is indexing.
It's discrete infinite.
It's discrete infinite.
I'm sorry. Yes, you're right. I go back. Q alpha. Yes, it's still discrete infinite. These are, if you wish, components of the classical field. The field itself would be vector valued, and Q alphas are the components of this vector field.
So Q is. Well, we can't go back to the previous page, but I'm asking, I guess, Q depends on X then as well, yeah? A point in space.
Q alpha for every value of alpha depends on X as a vector and on time.
Okay, so you're just suppressing the dependence on X right now.
Correct.
Okay. Second question, the definition is a definition of what? The action functional?
Action functional is this integral, exactly, subject to these initial the boundary conditions and actually initial conditions as well, for which we prescribe, in order to define the evolution of the system, the principle, variational principle that it should be minimized. So we will call a classical field configuration that corresponds to all this data, the one that minimizes the action functional when evaluated on that configuration. Okay. So I'll write this down. So classical, the solution, the state of the system for this setup. So the actual evolution is such, evolution simply means with respect to time, is such that, so it's given by that particular configuration Q hat, which minimizes, so it's the argument of the functional that minimizes the whole thing. Oops, keeps going to eraser. Subject to, so on all evaluated, taken from all those continuous paths, the way sketched in the picture, knowing about the initial value condition and about the boundary conditions. This is what this set stands for. It will take a little bit much to write it all. So I'll just say that that corresponds to all those possible paths. All right, so we are given a functional, we have to hope that it's well defined in the sense that with respect to this input, it is indeed positive definite, and therefore it does have, okay, shifted maybe, therefore it does have a well-defined minimum. And by finding that minimum, we have solved the classical mechanics problem for this classical field theory. So if I go back to the simple-minded one-dimensional field in one spatial dimension, which is the string, that corresponds to, I think I did write it down. It's right above. So that corresponds to, let's say, to make it honest, the action functional for this would be, I'm going to integrate from Q0 to Q1, and these are the boundary conditions. So integrate from T0 to T1, the space integration. I'm sorry, messed it up. Just 1 second. Erase. Let me think. Yeah, we can still do this. Q dot squared over 2 minus omega squared over 2 partial q in x squared dx dt subject to, this could stand for subject to as well. Q at t0 is some particular configuration you chose. I didn't specify what Q was. In this case, it would be just a number, I guess. And Q at T1 would be another arbitrary choice of boundary condition. So if you take this honestly, and actually one has to check for every particular choice of Lagrangian density that it makes sense, then the variational principle, assuming that the integrand is smooth enough, leads to the Euler-Lagrange equations. May I switch to a new whiteboard?
Yes, but before you do, so I want to make just another point of maybe clarification for myself.
Yep.
So the point you're making here is that this principle of least action, you're postulating, I guess, that the principle of least action that held for, well, mechanical systems with finite number of degrees of freedom still holds in this continuum case, yeah?
Yeah, it's a postulate. I mean, we
so
declare that this is the subject of classical field theory.
So you're now looking for the appropriate Euler-Lagrange equations. That's what's coming next?
Yes, this is exactly what's coming next, which is horrible, but I have to write them down anyway, so don't mind. Again, in full generality, what this leads to, it's not equivalent. I will comment on that. It leads to the following equations, set of equations. The time derivative of the following, why does it keep switching? Partial derivative of Lagrangian density with respect to the corresponding time derivative of the alpha component, the alpha f component of the field, is the same as partial L with respect to Q alpha itself minus, and here you have in general several coordinates, vector in space for coordinates. So I have j running from 1 to n, derivative in xj of this partial L with respect to the derivative of Q alpha with respect to xj. And that's true for all the components of the field alpha. Could be just one. So this is the full-blown form of the Euler-Lagrange equations for the classical field the way I've introduced. So this is going to be, for instance, could be something that describes the vector field Q vector of X vector, where X vector could live in, I don't know, R60, and Q alpha itself takes values into R2. It could be a two-dimensional vector that supported in a 60 spatial coordinates, and it also depends on time. It's not all that classical, but hopefully this illustrates the point. Okay. So for classical fields that people care about, there's always this description, but at face value, we don't necessarily see that directly related to this one example I provided here, which is appropriate for this something like generalized string. The equation we arrive at, I will actually make an example of the string model and actually derive the equations. Not surprisingly, are known as wave equations in the appropriate number of dimensions. So if I, again, connecting back to the example, if I had Q of X and T, as in the string example, then the Euler-Lagrange equations look like second order derivative of Q with respect to T. This is messy, I'm sorry. Partial minus that parameter Q omega squared, second order. second order derivative in X of the same field equal to 0. If you take just a comment, if you look at the Lagrangian density I had written from the very beginning for this problem, it was 1/2 q dot squared minus omega squared over 2 partial x q squared. If you look at it that way, at least this piece is absent from the equations. And there's nothing wrong with that, first of all, but this is simply not there because there is no explicit dependence of the Lagrangian density on the field itself. It's only through its derivatives. Of course, one can actually play the usual trick, which is part of the derivation of the order Lagrange equations, to use integration by parts. I won't actually spend the time here, but whenever you have something like well, second order derivative in x squared, the derivative of q with respect to x squared, like here, you can of course use integration by parts, and in so doing you arrive at an equivalent expression in the sense that it leads to the same solution, in which there is no dependence on the partial q with respect to x, but there is a dependence with respect to q itself. So I'm just going to add this comment that up to a contribution which is all dependent on boundary conditions alone, this happens to be equivalent to the form I'll write down right now, q squared plus omega squared over 2 q second order q with respect to x. And it's a simple application of integration by parts, and understanding that because of the boundary conditions we decided were fixed to begin with, the two integrands will provide us with the same solution for the same variation principle. Okay, that's not all important, but I wanted to make it clear. In this situation, if I chose that equivalent formulation, there will be, this piece will be missing for my integrand, but there will be a dependence on q itself. Any questions? Cool. So what does good physicists do? We'll think of any continuum, so to speak, as being made up of tiny pieces connected by strings, because quite literally any first order departure from equilibrium is described by this atomistic model. And therefore, at the fundamental level, any classical field theory boils down to the situation, the example I've just provided. If we consider more complicated features, and for instance, we take undertake things like averaging in space or clumping things together, then effective equations we arrive at will not look anything like the wave equation, but it's intrinsically and implicitly there for any classical field theory. I'm going to switch gears now, so last call for questions on this part of the story. How am I doing on time? Oops, this is taking far longer than I thought. So part two of this classical field theory, as I said earlier, has to do with Maxwell's equations for electrodynamics, but I want there to say electrodynamics because that's a real science with all sorts of important facts having to do with important phenomena, like we care about how electromagnetic waves propagate in real media, while Maxwell's equations don't actually tell us about that, which is a good thing because that helps us to see the mathematical structure in there. So there are first order vector partial differential equations for a pair of real three-dimensional real vectors called electric and magnetic fields, denoted E and B. And each of these will be a function on three-dimensional position vector in real space and time. Of course, they take values into R3. That's the way Maxwell and others actually wrote those equations, but we are going to fast forward and go ahead and write down the potential version, or rather integrated version of these equations through quantities that are not measurable. So I have to state here, let me add some color again. In the previous picture, everything I had said so far, this was supposed to be measurable. it's something you can actually go in, and whether imaginary or not, there is an experiment you can perform to figure out what is that quantity at that point and at that moment in time. Likewise, these are measurable quantities. This is not taking values in, it's just that the feature is that they're measurable. And that's, of course, building up towards the concept of observable that we will talk about at the quantum level of this progression. Now, the quantities I will switch to are not measurable in themselves because they are like antiderivatives or primitives, and therefore, if nothing else, like good students of calculus, we recall that there are integration constants which we can quite often say nothing about, so we don't know these quantities in full. There is no way to directly measure them unless we make some convention on those integration constants. So I'm going to switch to potentials. There's a scalar valued function of space and time, just the one, known as electrostatic potential. And a vector valued triple of such components, known as vector potential. Right, and they are proposed as good choices for, like I said, quantities whose first derivatives combine to give us the electric and magnetic fields. So let me see. So we have 15 minutes, right, Aidan?
Yeah, you can go a little bit over probably because we started a little bit late.
Yeah, but it's not a good habit. So I will probably not say much about these things at this stage. I will just to make the point for the day. I will simply say that the equations we call Maxwell's equations, coupled with an overall condition that we understand as conservation of electric charge, lead to the following common description. And let me know if you want details. Right. So in an area of space where there is no charge density or density of electric currents, we arrive at, not surprisingly, I guess it's physicists, so I'm going to write gradient squared, acting on curly A. Well, curly A is the vector at this stage kind of formally defined four-dimensional vector consisting of all the components of the potentials I just introduced earlier. And for it to be an equation, this better be equal to 0. So this is where there is no charge density or flow of charge, something we call current, electrical current density. And if one wants to know why do we care about the equation in such regions in space-time, it's because, well, for the most part, like between where we are and what Greg is on some distant planet, it's a fair approximation that there is no electrical charge to speak of, something like what we might think of as vacuum, and yet this field does exist and it does propagate, does evolve. So for the most part, it's like that. Where there are charges or charge densities, the right-hand side isn't equal to 0, but that's not a big deal. And we can think of those as being negligible as far as volume in space-time is concerned. So the point I've tried to make so far is that in both situations, classical field theory for mechanistic purposes and Maxwell's equations, homogeneous Maxwell's equations, we arrive at the single equation, whether in one spatial coordinate or several, known as the wave equation. And I probably wrote stuff that people haven't seen here on the very bottom, so I will, if you don't mind, repeat that. I call by curly A the vector that consists of at once of the electrostatic potential and of the vector potential. Then if there is no charge or density, current density in some region in space-time, we have the following equation. describing evolution of this system. Just like for the field, for the classical field. Wave operator, wave equations, in this case for the components of the electromagnetic potential. So any questions about this claim? If people are really interested, then I can actually provide some slides which are coming from my notes where the details are discussed in full. But the point I'm discussing is the following: pre-relativistic theoretical physics, which is ignoring at this stage anything having to do with thermodynamics, was in fact going naturally to a description that's basically fundamentally the wave equation, and that is surprisingly fully relativistic. So I will now, with this background, pose the question that at the time wasn't considered to be all that important, but then it turned out to be the most important question. What are the transformations? Find transformations, quote unquote, because there's not all of that well defined, on the spatial and time coordinates, leaving the wave equation, or rather the wave operator, unchanged, invariant. All right, so why would one think about that question? We have to go back in the sense of evolution of understanding in theoretical physics. In fact, we have to go back all the way to Galileo Galilei, which is not a bad thing to do, because quite naturally we'd want the equations or the principles that they came from, that we base the whole theoretical description on, to be in such a way that we shouldn't worry on the choice of coordinate system used to derive them. And the only way this can happen is that in such a way that if you change something, you won't see a difference in the actual equation that you're trying to solve. So it makes perfect sense to ask, what are the space-time coordinate changes that will leave this operator look exactly the same with the new choice as compared to the old choice? All right. I took a long time to get here, but this is the question connecting the pre-relativistic 19th century physics to the beginning of 20th century.
Real quick, Professor.
Yep.
This is going to lead into like symmetry.
Well, I want to be already pedantic. Symmetry is something we reserve for yet another kind of transformation, which turns out to have it's best understood or kept only for those transformations which have to do with internal structure of the state of the system. And by that I mean the following: the quantum fields we're building towards are at the same time related to these transformations in space-time, and know about more structure than that, which is sort of hidden to us. There is something we could call, and we should call, internal structure, or internal symmetry. So from that point of view, I'll be referring by symmetry to those transformations that have to do with structures I haven't talked about yet. And instead, when we talk about coordinates, space-time coordinate transformations, we will be talking about invariance. Okay? It's true that I can think of a system which is, by construction, explicitly invariant with respect to rotations of the spatial coordinates, the vector in space, right? Which gives me the position in R3. And superficially, we would say that that system has spherical symmetry. Is this what you're thinking about?
Yes, just I guess like the invariant, like something being invariant. I was relating that to symmetry to some extent.
I know, and it can be a bit confusing, so I will try to be pedantic here and only reserve symmetry for what we call internal symmetries, because, for instance, fundamental particles like the electronic field will know at once about invariance in space-time and internal symmetries of a different kind, which has to do with it being one of three such particles making up a family that we call leptons. And from that point of view, we will not want to distinguish between the electron field, the tau field, and the muon field. They're like cousins. And from that point of view, they'll be seen as being equivalent. That kind of internal symmetry is not captured by what I'm saying here. It's the same kind of linear algebra at the end of the day, but there is no space-time story to tell in that situation, right? Do you understand?
I see, yes.
I'm not showing you what I'm saying, but that's basically the answer. So this is, I will only try to refer to this property as being an invariance of an object, in this case of the wave operator itself. Okay?
Understood, thank you. Yeah.
Cool. So if I want to write this wave operator in some form that leads me to a linear algebra, because this is really the physicist's best friend, I will first of all give it a name. This is what we sometimes write it like in books. This is D'Alembert's operator. Or the wave operator, and it's the one I already wrote. Second order derivative in time minus gradient in spatial coordinates squared, which is another name for what we know as Laplace operator. Why does it keep switching? Sorry. This is Laplace operator in Rn, quite generally. So this is the D'Alembert operator in n+1 coordinates, one of them being what we call time, and the other n being homogeneously spatial coordinates. The question is, what kind of space-type transformations can I apply that will make it so that this operator won't change? And again, for the last time, is it clear why we care about it as being a unifying question relevant to anything that people cared about before full-blown relativity theory came about? Because this invariance was there already in Maxwell's equations 50-some years before Einstein. So if I write this in the following linear algebra form, I will, for now, already set C to 1, because we know we can, but mathematically it wouldn't be a big deal anyway to absorb that in the definition of time. Then what we're looking at is this, I have the row vector, so to speak, dt gradient. Again, the same vector of partial derivatives written in column form, and in between these two, there'll be an n plus 1 by n plus 1, in this case 4 by 4 matrix, which contains all the relevant information. In this case, it's just 1s, 0s, and -1s. So I have the way I wrote it, a bunch of zeros on the first row in the first column, and then in this 3 by 3 submatrix, I simply have negative the identity. Right? Is it clear to everybody what I'm saying? If we multiply formally these partial derivatives, then we get D'Alembert's operator. And the question posed is the same as asking, if I now go from this choice of coordinates TR from my original system to something else, let's call those tau and rho. I know it's horrible, but a different choice of space-time coordinates. We want to know what is the most general such transformation which will make it so that the D'Alembert operator will look identical to itself in the new coordinates. And we will say that only coordinate systems, so to speak, that have this property that can be generated from each other by requiring this invariance are acceptable in the description of that particular physical theory. Again, this goes all the way back to Galileo Galilei, and the answer he found, looking at pre-Newtonian mechanics, was something we nowadays call the Galilean group of transformations, which is a limit of the proper description that I'm talking about, which is the Minkowski, Einstein, a few other people, group of invariants. And I think I should probably conclude for today. So this is the question that one can actually start from in what would be like talk number 1 in this series. This was building towards the question. Nathan, do you think it's a good moment to stop?
I think it is. So the question is, what sorts of transformations leave, well, the above operator, Dellenberg's operator, invariant under?
Exactly.
Okay. So, oh, go ahead.
Oh, it's kind of a joke question, but why did you choose that signature? Why not? I thought we were on the East Coast. Your metric in between the column and row vector there. You went 1 and then -1, -1, -1. I thought we on the East Coast went -1, +1, +1, +1.
I got it. It's a good joke, but the problem is I kind of like to. We will want to refer to the associated object made up of differentials. So if you think of the same thing, but instead of writing the partial derivative in TL, write the differential in time, and in here the differential in coordinates x, y, and z. I will want to think of that as being a proper metric in the sense of Gauss in this 4-dimensional space-time. And if I made the other choice, it wouldn't be. It would be anything but, because if you were to evaluate that, you would get a negative quantity all the time. So if I want to push this, which I will write down, c squared dt squared minus Euclidean 3-dimensional metric dr squared, I want that to be a proper metric, as in positive definite. And if I make the other choice, which is so there are 2 conventions, and typically speaking, not always the 2 statement. General relativity books and quantum field theory books use opposite conventions. Point is, typically, if you want to have that as the proper way to generalize infinitesimal distance in Euclidean space, then there is no other choice. Is this answering your question?
Yeah.
I want this to be, in the sense of operators, positive definite.
To be clear, like that is a very, very confusing thing. I think sometimes is that there is when it comes to the Minkowski metric, there are conventions where you choose differently, right? And sometimes it's more convenient to use one as opposed to the other. This is correct.
Well, again, if I want this to be positive, I really don't have a choice. There is no convention to choose from any longer. I mean, there's no other way to put together these numbers in such a way that you get something that can be understood as infinitesimal norm squared, right? So the reason for people's choice being different in some books has to do with the number of times they want to worry about changing the sign, basically. And it really depends on what they are doing there. But in a fundamental sense, this is the only correct choice. Now, I will discuss next time how to extract from a generic positive definite hyperbolic metric, because this is what this is. It's a hyperbolic metric, like the hyperbolic operator, wave operator. So how to extract from a positive definite hyperbolic metric of this type the effective 3-dimensional metric that's associated with it. So I think what's confusing to most people is an artificial problem, because they look at this and they think, oh, but if I set dt to 0, I'm getting something that's not meaningful, because I'm not getting what I would expect to get, which is the typical choice of metric in 3 space coordinates, right? In R3. But there's not the right way to do it. I'll discuss this in the context of special relativity. Actually, general relativity is even better, in which if we generalize this further, this to be some matrix, symmetric matrix G of entries let's see how that went. Gij. These are the row and column, if you wish, entries of that metric. Then what we're writing, actually, take it back. I'll do it Gij. And this would be where ij run from 0 to 3, 0 being time. So if I write this as my generalized hyperbolic metric, restricted to that cone, interior of a cone in space-time where it's positive definite, that's a handful, I know, but I had to say it. So from this, we can extract the actual spatial component, which is not at all, I want to stress that, is not at all what you get by removing this piece from the previous expression. Because the way you define distances in space alone has to be understood in the sense of an experiment where you're sending a signal from one point to another point, and then information has to travel back. And then these two people, the observers, use the information to figure out what's the actual space distance between them, right? When you go through that, what you arrive at is perfectly well defined, meaningful. Choose blue. It's something that looks like, I might get wrong, but G0 alpha, G0 beta, minus, sorry, where is it? G alpha beta, dx alpha, dx beta, where now these indices are just spatial indices. That's the effective reduction of the metric Gij to the spatial hyperspace, hyperplane, whatever, in R4 for a choice like that, for a generic choice like that. And if you go ahead and apply this to the Minkowski metric, you see that you are getting exactly what you'd expect, precisely dx squared plus dy squared plus dz squared that we've known since the time of Pythagoras, basically. Does it make sense? So the choice I made with the minus in front of the spatial part of the matrix is exactly what you need to turn this into a positive quantity and therefore arrive at the sum of squares of differentials of x, y, and z. Have I lost you?
No, I understand this.
Okay, so this is simply this is a theorem. If you want, we will look at it. That's what measurement-based notion of distance in special general relativity, in this case, really gives you for that distance in the restriction to R3.
I see. I'm familiar with mostly so R2, let's say, like we can talk about isometries in R2, and then there's an analog within, you know, hyperbolic space, two-dimensional hyperbolic space. And then you can take this to Minkowski space and we can construct the metric basically using isometries, things like this. Like it's a very algebraic approach, but I don't know. I'm kind of like, that's kind of how I'm thinking about things. I'm trying to reconcile all this based on algebra in some sense.
Yeah. Well, there's nothing wrong with that, but I was trying to get to that by a more intuitive approach, a more, you know, evidence-based approach, in the sense that we will be saying things like there is a limiting speed for all phenomena, observable phenomena in the universe, and that's the speed of light in vacuum. And we believe that this is a maximal speed. And then starting from there, if you wish, we will fall squarely back on what I'm discussing right now. But I was trying to say that even pre-relativistic theories, especially Maxwell's equations, already had this fact built in. Asking questions like, what is the largest group of transformations of space-time leaving the wave equation invariant was more than enough to arrive at the Minkowski metric, way before he did it himself. Okay, but of course, we then can add more actual experiment related information, something like what we get by doing measurements along the lines of Michelson and Morley. And then we conclude that, moreover, there is evidence pointing to the fact that we have to impose that the speed of light in vacuum is an invariant. And then we conclude yet another time, second time around, that this is the only possible choice for a metric in empty spacetime. Okay?
Okay. Yeah.
But at this stage, we get it by simple geometric considerations. Right. So sorry if I went over time, and sorry if I was more confusing than I intended to, and hope to see you again.
Cool, thanks a lot. So someone is calling me. Okay, there we go. So if there's no further questions, are there?
Okay.
Then thanks again, Razvan. He'll be speaking again next week, continuing this talk. I'm going to stop the recording.